Hello everybody, Math Hobo here, and today we're going to be talking about the gamma function. But before we talk about the gamma function, I'm going to preface it with a little question. What is half? No, that's what is half factorial. Well, you might say, well, Math Hobo, are you crazy? Are you completely out of your mind? Well, no, not completely, because I believe that you can take the factorial function, which is only defined over positive integers, and you can actually extend it. You can sort of transform it to be defined over all the real numbers, and in fact, perhaps even all the complex numbers. So we'll get into that later. But what is half factorial? Well, it turns out that half factorial is actually root pi. How crazy is that? Where's pi coming in the picture? I thought that only came up with circles. Well, it turns out that pi is pretty much ubiquitous in all of mathematics. It turns up everywhere. The same thing as e. But now let's begin talking about the gamma function, which will allow us some insight into this problem which we have of defining factorial over the set of real numbers. So the gamma function. So the gamma function is given as capital gamma of z is equal to the integral from 0 to infinity of x to the power of z minus 1 times e to the negative x dx. Now this looks very scary. It's a big integral with some weird symbols and all, but how does it relate to the factorial function? We'll get into that soon. So what do you say when you see a big integral like this? Well, sometimes you say, oh, well, let's do integration by parts, and that's exactly what we'll do. So we'll set this term, x to the z minus 1, is equal to u, and this term, e to the negative x dx, is equal to dv. And then integration by parts, if you remember your calculus, is integral u dv is equal to uv minus integral v du. So let's erase this stuff. And let's take uv minus integral v du. Okay, what is u? U is x to the z minus 1. So u times v. So this is dv, so v will just be the integral of this guy. And that is just negative e to the negative x. Yeah. And this is taken from 0 to infinity. Those are the limits. Yes. And so then that is minus integral v du. So again, v is that, so you get plus integral from 0 to infinity, and v is negative. So actually let me clarify that. So we have minus integral from 0 to infinity, v, which is negative e to the negative x, times du, which is just the derivative of this guy, which is simply z minus 1 into x to the power of z minus 2, and then dx. So when you have minus minus, you get plus. So then you get plus e to the negative x times z minus 1 times x to the z minus 2 dx. And well, remember, this is equal to gamma of z. Now let's evaluate this guy. What happens when this expression you plug in x equals 0? Well, you get 0 over here, and since it's multiplying there, it's 0 there. Now let's check for infinity. Well, in infinity, this guy goes to infinity, but that's not a problem because we have e to the negative x, and e to the negative x when x tends to infinity is simply 0. So you get 0 in both cases, and this entire term just cancels out. So we can forget about that guy. And then we have gamma of z is equal to integral from 0 to infinity, that thing. And well, what can we do now? Well, since this z minus 1 is essentially a constant term because we're using some z, and it's integrating in terms of x, so this is essentially a constant term, we can just pull that out. So we get z minus 1 into integral from 0 to infinity, e to the negative x, x to the power of z minus 2 dx. And hey, you say, this looks a little bit familiar. And that's for a good reason, because this is essentially gamma of z minus 1. Because if you think about it, the way we define gamma of z to be integral from 0 to infinity x to the z minus 1 times e to the negative x dx, this is the same exact thing, except it's x to the z minus 2 instead of x to the z minus 1. So that's gamma of z minus 1. And so the crazy thing is, if we replace this entire big integral with gamma of z minus 1, then we get our functional equation, is what it's called, which is that gamma of z is equal to z minus 1 into gamma of z minus 1. That is our functional equation. And what can we derive from this functional equation, you say? Well, let's take a look back at the factorial function. So what happens when you have some function and you multiply that with the number before it and multiply that with the function of the number before it? Well, let's plug in factorial. Let's see, this looks vaguely reminiscent of factorial. So z factorial is equal to z minus 1 factorial times z minus 1. I switched those two around. But that doesn't really work. That doesn't really work. And for good reason, because gamma of z is not exactly z factorial. It in fact is z minus 1 factorial. So you have z minus 1 factorial is equal to z minus 1, z minus 1 into z minus 2 factorial. Right. And that definitely works because you multiply z minus 1 times z minus 2 factorial and you get z minus 1 factorial. And that is exactly that. So what we've realized here is that the gamma function is actually just a factorial function. And in a very vague sense of the term. But the great thing that we can do is now we can plug in gamma of half. And I will get to this in the next video. Thank you very much for watching.